Now, what I want to show you is that what happens when we increase the length so that we actually have a discontinuity. So what happens is that although I'm using finite volume, it's still non-trivial to resolve the shockwave. We have to do something a little bit smart to ensure the stability even for our finite volume schemes. Okay, what you can see is that now my interface seems to be blowing up, right? So basically, instead of resolving the shockwave, I actually have a basically oscillation. It's actually a volume by volume oscillation going on. So my solution around the shock just keeps getting larger and larger until the solution now fails. So this tells us that although we are using finite volume, we still have to adapt our scheme. In particular, we cannot ignore the principle of upwinding. Okay, so all the stuff we learned in finite difference still applies here in the sense that we want to look upwind of the solution for information. Okay, so now if we examine our flux approximation here, we are using the average both on the left and to the right of the interface. What if we use only the information towards the upwinding side of the interface? Which means if my solution is positive, I want to use the average on the left. If my solution is negative, the wave speed is going towards the left, I want to look at the upwinding direction, which is on the right. Right? So this is what we are going to be trying next. So instead of just taking the average, I'm just going to say the U interface L. Oh, let's actually still take the average and base the average on base the direction of information on the average. So my U at the interface is either going to be U if, so U, remember, lies on the right of the left interface. So it's going to be U times the average being negative. Okay, and it's going to be my, okay, so let me actually say U interface L right is equal to U itself. So that'll be easier to understand. So that lies on the right of the left interface. What's lying on the right of the left, on the left of the left interface is actually the left value. So which is this. So now here you can see that the average is U interface L R plus U interface L L. And now my U interface L is actually going to be my U interface L right times the average being less than 0, which means the wind comes from the right. And if the wind comes from the left, it'll be U interface L average greater or equal to 0. Okay, so that's going to be the U interface L I use for computing the flux function. And I'm not going to change how a finite volume scheme works. That'll be an upwinded solution. All right, now let's, if I reinitialize and I'm going to rerun what? Line 25. Oh, here, okay, yeah. Point, let me reinitialize and rerun the visualization. Okay, and see what happens when the shockwave starts to form. Okay, now we can see that we actually could resolve the shockwave, right? there are no line connecting between them. That's because we are actually only visualizing the volume averages. And there is actually a discontinuity, right? No solution lies between these two values. All right. So this is basically how a finite volume scheme works when we have a stable approximation of the interface flux. Okay, let me just give you a little bit more information, but now I want to answer the question of what if we have some non-trivial boundary condition. Okay, so let's actually go back to our previous discussion of the contours of the characteristics, because this is actually very important in determining what kind of boundary condition it is appropriate to specify. Okay, and in particular, let's actually imagine we are solving a case where all the characteristic speed is positive. And do you remember when the characteristic speed is positive, how would the contours of the solution go? Right, we have du dt plus g of u du dx is equal to 0, and this thing is greater than 0. How, if I have an initial condition, how would the contours go?
It goes up and to the right.
Everything goes towards the right, exactly. So the slope might be different, but it always goes towards the right. Okay, so now let's imagine we actually have non-trivial boundary conditions. Let's say I'm looking at a domain like this, okay? And this is actually my left boundary. This is my right boundary. I'm only solving the equation within the boundary. The question is, if I look at the right boundary, it's actually very strange. If I actually force the solution here to be something, can I actually force it? Can I actually specify a boundary condition here and say that, oh, I want the value here to be 0, while the value here might be 1? It doesn't make sense, right? Because I know along each characteristic line, the solution has to be exactly the same, because this is a contour line. And there is no way the solution here can be forced to be 0 if I already have an initial condition here that says the solution is 1. No, the solution here is going to be 0 and it's going to be 1. There is no way to force the solution here. Do you agree?